Well, good evening, everybody. Thanks for the introduction, Mark, and I'd just like to say what a privilege it is to be here at the Royal Aeronautical Society and presenting the Sopwith Lecture tonight. And also, as a personal tribute, I'd also like to mark my late stepfather, Jeremy Fermo, who is a lifelong member of the Royal Aeronautical Society and spent his life working as an aeronautical engineer and then a mechanical engineer. And he was always slightly disappointed with my career choices in that I hadn't followed him into what he called a proper job like he'd done, and I decided to go and become a stupid pilot, which was his words, not mine. But anyway, now I'm here in the hallowed halls of the Aeronautical Society. I do hope that he'll be looking down on me and will offer me some forgiveness. So as you can see from the grey hair, I've been flying helicopters now for 30 years or more, so I'm well placed, in fact, to sort of offer what helicopter pilots have as nightmares. And it's not Daleks, it's not Freddy Krueger, it's often something like this. That was a video of a firefighting helicopter in Spain, a twin-engined 412 aircraft suffering an engine failure about 20 feet over the water. And the sort of harrowing sound for us is the sound of the turbine engine spinning down, shortly followed by the rotor speed drooping and the aircraft hitting the water. So not a great a place for a helicopter pilot to be. So I'm just going to have to do some more IT faff.
Would you like to still try?
So, no, that's good. Okay, I'm in a better place now. Okay. So I'm here today to talk about helicopter engine failures, and I'm going to be looking at the flight test techniques that run with that. And just before I start, I want to narrow my subject down quite a bit. So I'm going to be talking about twin-engine or three-engine aircraft, so multiple-engine aircraft, not single-engine aircraft going into auto-rotation. And I'm also going to be concentrating on engine failures in the hover environment and the low-speed environment, not engine failures when you're in forward flight, because engine failure in forward flight in a helicopter is rather dull, really, so that's not the subject matter that I'm going to be concentrating on. Obviously from a flight test department, I'm going to be talking about how we build performance data and then develop the flying techniques for those engine failures and then draw them into a flight test campaign. So that's gathering data for our performance manuals and generating the advice on the flying. I'll give a sort of brief overview of the recovery techniques that we use in helicopters when you suffer an engine failure. And then I'll talk about the testing methods that we use. So computer modeling, simulator profiles, digital engine control. And I'm going to wrap all that up into how we go about executing a practical trial, if you like. So I do realize that a good proportion of the audience won't be from a helicopter background, so I apologize if I use too much helicopter speak. If I keep repeating something you don't know what it is, please stick your hand up and I'll explain. But I will try and keep this or try and explain some of the more helicopter terms for the benefit of the general audience. I apologize to the helicopter specialists that are in the room or watching if it does sound a little bit noddy. Right. What I thought we'd start with then is a case study in limited power, and this is really where my kind of interest in this subject grew. So what you can see on the screen there is a rather forlorn-looking Sea King. It crashed in Iraq in 2006. And my involvement came as part of the Board of Inquiry team that was sent out to investigate the nature of the accident. And as you'll see from that, revealed some interesting things about dealing with a limited power situation. So I'll talk you through the accident sequence. What we've got here is a helicopter landing site in the middle of a compound, surrounded by a number of 15-foot walls, blast walls. So one round here and some more over here. And along the side here, we've got the edge of the compound. So that's a sort of 20-foot wall surrounding the edge of this isolated compound in the desert. And also over here is a Sanger, a sort of 30-foot watchtower. So at the time of the crash, the aircraft was flying was due to take off as part of a formation. So the aircraft was ranged on the spot. The first aircraft lifted, and then shortly afterwards, they lifted. Just as they crossed the wall, they found the aircraft starting to sink towards some wires in front of them, and so they turned right to avoid those wires. So there was their initial power loss, which was effectively caused by the downdraft of the other departing aircraft. So actually, it wasn't an engine failure, but the reason it's relevant is the aircraft was extremely heavy at the time. So now, having turned away from those wires, the pilot then saw the watchtower over here, and so he continued his turn round the corner, and as he got over the next set of walls, he saw the wall of the edge of the compound coming towards him. He hadn't climbed above any more than sort of 15 feet at the time, and as he saw the wall, he then flared the aircraft, raised the nose to bring the speed back of the aircraft, and at that point, the tail hit this wall here, and the aircraft crashed. So that was the crash. But the bit that was interesting for me was after that, we came back to the UK and then went into a seeking simulator, and were able to recreate the landscape of the crash and the environmental conditions, the all-up mass and everything involved in the crash, and then have a go at flying it. So interesting, one of the statements that came out was that during this accident sequence, they didn't pull the maximum power available in the aircraft. And so when I got in, I was the first one to have a go, if you like. Similarly, I crashed, but interestingly, I didn't pull full power either. And I put that down to what I call the armpit factor. We're not used as helicopter pilots to having the collective lever, the power lever, right up under our armpit, because normally by that stage you're over-torquing the aircraft and therefore damaging it. So it is very unnatural for a helicopter pilot to raise the lever that much. So I didn't achieve full power either. I was sat with a young lieutenant next to me who was also on the board of inquiry, and having seen me do it, he said, "I'll have a go now." So he had a go. What he did is, round at about this point, he pulled the lever very quickly right up into his armpit, giving full power from the engines. However, that also put a huge amount of pitch on the blades. The rotor speed decayed very quickly, and he crashed way before I did. So I sat there looking slightly smug, but not that smug, because we'd both crashed. But we realized that there was a kind of midpoint here in terms of our management of the collective lever, about getting to a point where we could get the maximum power from the engine, but not get to the point where the rotor speed decayed so quickly that we would crash. So we played with that for a bit and found the happy medium. And what that was basically was to pull the lever up over about 5 seconds until you heard the rotor speed just start to decay, and stop moving the lever, and then you're in the perfect position, maximum power from the engines with a good rotor speed. And using that technique, we were able to get ourselves to just about scrape over the wall at the edge of the compound and fly away. However, there is another factor that all helicopter pilots will know, and that is called translational lift. So as you build speed above 10 knots, 12 knots airspeed, you start to get a dividend from the induced flow being blown away from the rotor disc, which means that you need less power. So getting that airspeed on is quite important. So then we started flying this profile, doing our rotor speed management, but also dipping the nose forward to adopt a gentle accelerative attitude in order to build the speed and therefore give us that translational lift. And using a combination of those two techniques with a nice gentle increase in attitude, we were able to really get the aircraft to climb away from this kind of point here and build speed coming up over the wall. So we were clearing the wall by 50, 70 feet on some occasions. So the combination of those two techniques was effectively took us from a point of crashing the aircraft to being able to fly away safely. And the reason that I've brought those up is because those are the two sort of fundamental key features about engine failure testing and being able to develop a technique for a pilot to fly away. So Surviving an engine failure then. In that case, did the pilot use all the power available? No. How do you get the maximum power from the engine? I drooped the NR a little bit, but no more. How important is the rotor speed? As we saw the lieutenant did, if you don't maintain the rotor speed, it's all over very quickly. And translational lift, the airspeed is the other factor. Another thing to consider is don't get into that position in the first place, and you do that by the use of a performance manual, planning before a sortie, and making sure the weight of the aircraft is commensurate with the environmental conditions that you've got and what you're trying to do. So we do that using a flight test campaign. So we have some clever people on the left with computers, screens, and a lot of intellect. They're the engineers. And over here on the right, we have the stupid pilots, apart from that one, because that's Mark, and he's my boss. So flight test, air crew, and the engineers to go with it. We start at the campaign building those performance tables and data. And that is done using a computer. It's done using a computer model. So Leonardo has two models that it uses. The HAPS one there, the Helicopter Airfield Performance System, was developed in the 80s. It's a two-dimensional model. And then in the 90s, as a consortium with 4 other helicopter manufacturers, a new modeling system called Europa was developed. So those models effectively use very complex calculations. If you thought you were coming here to a lecture tonight to have someone explain how those work, then you'd be wrong, because I don't know. Clever people do it with computers. That's about as far as my knowledge goes. But they use theoretical calculations. That's refined by some of the world rig testing that we've got. And then they feed in trials data into that model to further refine it over the lifetime of the helicopter. The model will cover a spectrum of altitudes and temperatures, so density altitude in other words, and clearly a spectrum of weights of the aircraft as well. And it generates what we call the power carpet, which basically covers anything that you want. So you can put any condition you want into the model, and it will give you the power that is required for the performance of the aircraft. So we then go and set about validating that. Before I jump too far ahead of myself, I should mention engine power output, because when we're looking at the rotor performance of the airframe that we're going to go and test, effectively the engine power is assumed as a constant. It comes from the bench testing that the manufacturer does. We use the figures. We don't necessarily test the engines as such. We accept the manufacturer's data is going to be good, and that we will have a uniformity of engine performance across the density altitude spectrum. What that doesn't necessarily take into account is engine degradation. As we know, as time goes on, engines get less efficient. So there's an element of that. And also, you lose a bit of engine power as it goes through the transmission, so what we call installation errors. So those are the factors about the engine. There's just a couple of terms up here at the top that I'm going to refer to later on, which again for non-helicopter background people might be a bit confusing. So we talk about our power ratings in a number of terms, but the principal ones is the max continuous power that you can pull. So that means you can pull that all day continuously. And typically for a helicopter that will be around 100%. Okay, we then have a contingency rating. That might be a transient rating. And we'll have a further contingency rating when you lose an engine. So when you've lost an engine, the total engine power now going into the transmission is less, which means you can ask the good engine, the one that's still going, to give you more power. So that maximum contingency, one engine in operative rating, will be in the region of sort of 130, 140% torque compared to the 100% torque that you would normally only continuously pull. So those are two sort of terminologies. Have I explained that sufficiently? Good. Right, so that's the engine. So as I said, once we start on the flight test campaign, we've got a model, and our task is to go and effectively validate that model, check if the model is correct by gathering real-time data. But obviously that power carpet across a range of temperatures, weights, density altitudes is an enormous task. So to do it practicably in a reasonable amount of time, we are just trying to spot check the data. So using different weights in the aircraft and using a referred technique to try and get to increased altitudes. But to really get a comprehensive check, you need to go to different sites. So depending on the funding of the trials program and depending on the time that you've got, certainly start at a low site first. That's the basic data. And then if you can, you'll go to a medium site, about 5,000 foot density altitude. And then you can go high, go to sort of 8,000, 10,000 feet. However, that is more expense on the trial. And what you're starting to run into there is, rather than rotor limiting properties, it's engine limiting properties. And if you had loads of money and all the time in the world, you'd also go to a cold site, but I don't think we do that very often. So that's how we go and validate the model. The techniques that we use are basic helicopter performance techniques. So this is a picture of tethered hovering. I hope you can see there's a cable running down from the aircraft, attaching it to the ground, and that allows you very quickly and easily to measure the performance of the aircraft at a range of weights. We have a strain gauge attached at the top of the hook. That measures the force that you're pulling on the hook. You add that to the known weight of the aircraft, and therefore you have a pseudo aircraft mass which you can compare against the torque figures in the aircraft. So that is for a static condition. We also flight test up and down the runway using a GPS to Doppler-based sort of system to fly the aircraft at different heights and at different ground speeds in a zero wing condition in order to derive data for increasing speeds within the low speed environment. So that allows us to validate our basic model, and we can then go back, give it to our engineers and say, right, put that in your supercomputer, make sure it all checks out, modify the model if required, and then we use an iterative approach for them to develop the techniques that we're going to need to use to recover from an engine failure. So they fall into largely two categories with some variations. The first is a flyaway. That means that the power to weight ratio is sufficient with the height that you have of the aircraft to allow it to fly away into forward flight without coming in contact with the ground and flying away safely with one engine not working. The other is the flip side of that, where you don't have enough power and the aircraft it needs to effectively land. You can't continue flying, normally called vertically rejecting the aircraft onto the ground. So those are the sort of two basic techniques that we've got. For classification of civilian aircraft, we also use a number of other techniques. So an unrestricted departure from an airfield, a sort of confined area short field departure, or indeed operating from a helipad. So similar sort of flyaway vertical rejects, but modified by the landing site that you're going to do. And we need to go and test all those profiles and make sure that the model answer is correct and validate that model. So what does a flyaway look like then? Well, it looks a bit like this. Here's a diagram I prepared earlier. So the aircraft will be sat in a hover doing its roll, or it could have been taken off and backing up as part of its civil departure technique. The engine then fails. Lightning reactions of a seeking pilot. I know it takes about 2 seconds for a helicopter pilot to work out what's going on before they do something, but that is a genuine time delay that is appropriate for when someone is not paying full attention to what they were doing. So 2 seconds is about right. So the engine's going to go, the rotor speed will decay, and the aircraft will start to sink. The pilot's then going to react. If we go back to our worked example, he needs airspeed, so he's going to adopt an accelerative attitude, dipping the nose forward, and he's also going to control the rotor speed to the optimum to try and get the aircraft to stop that sink towards the ground. So as the speed builds, the aircraft will level off, and you'll get to a position where you can start climbing away from the ground. So that's the basic flyaway profile that we would use. For the practicalities of the flight trial, We also need to have low wind speed, because wind speed brings in the translational lift effect that I discussed, and so that then messes up your data. So one of the constraints is that we need to work at 3 knots wind or less. And when we actually start flying these, obviously what we don't want to do is crash straight away. So we start nice and high, and then fail the engine, perform the flyaway maneuver, and then see the amount of height loss that we've gone, and then incrementally work our way down until we're leveling off at 50 feet and not entering into the ground cushion, which again affects the data. So we're flying those techniques. They need to be consistently repeatable, and that is actually quite hard for the pilots to do. So adopt in that dynamic situation, monitoring the lever and adopting a steady attitude and holding it throughout the flyaway profile. Sometimes we don't get it quite right, but that's quite good, because at the end of the day, when you collect all your data, you've got a good scatter of data there to go away and analyze. Those are the flyaway sort of profiles, and obviously you can turn that into a science project and do as much as you can, but there is limited time and cost in a trial, so you have to try and again do a spot check of the data. I talked about vertical reject, so that's the same, but if you remember, these I said we're actually going to land the aircraft. So the problem with that is on a trial, if you break the aircraft, you've now broken the aircraft and the trial's over. So it's quite a tense time for us pilots as you're suffering that engine failure, descending towards the ground. You need to make sure that you don't get to a position where you actually hit the ground so hard that you break it. And the way that we do that is we monitor the rotor speed and the decay in the rotor speed during that descent to the ground. And when it gets to a certain point, we'll know that we'll then not go any further in the testing. We've reached the limit, if you like. It's a visual maneuver, so we need to make sure the visual cues work well for us. And here's a video which shows, so it's an aircraft out in Cuneo. It's doing a helipad departure. It's just suffered the engine failure there, starting to descend towards the ground. As it starts to zoom in, just make sure you're watching the compression of the oleos on the wheels. So the pilot's now flaring off the speed to reduce the rate of descent slightly, leveling the aircraft, and then using the collective to cushion on. And at the end there, you can see there's quite a thump onto the main oleos. So when you're sat in the aircraft, that doesn't feel very comfortable. It feels like you're about to break the aircraft, and so that's the end point. That's as high as you will go to start doing that vertical reject technique. Here's another video, relatively similar, but this is an approach technique. And so you'll see here again, the aircraft descending with the engine failure. The pilot's flaring the aircraft to use the flare energy to lower the rate of descent. But you'll notice there how close the tail is to the ground. So in that final stages of the maneuver, you're bringing the tail pylon very close to the ground. And if you get that wrong again, you break the aircraft, the trial's over, and then you are going home with your tail between your legs. So those are some of the examples of vertical rejects. What I wanted to move on to now was what can be used to help us. And the first thing we use is simulators. So it depends on the maturity of the simulator within the program that you're working on. But generally, the simulators will have used some form of the power carpet to model their performance data, although others have real-life data they've picked in, fed into the computer program within the simulator, so it's not always the same. So the level of sophistication does vary. But going in the simulator before you go and fly the trial allows a certain refinement of technique. It allows us to try different techniques in the simulator so that when we get on the trial, we've just got more knowledge, and it means that that spot checking can be done far more efficiently and effectively. We can also look at the difficulty of handling the maneuvers, and that will give us some idea about what we're going to go and try and fly on the trial. So simulators are also nowadays very clever, so we can use an automated analysis where we will ask the simulator to run effectively a flight profile for us and get them to modify one parameter at a time, and that will allow us to analyze what we will get. So we can see here, this is a graph of pitch going from about 7 degrees nose up down to just beyond 15 there. and we're adding delay times here. So we've got different coloured lines. Obviously, the dark blue line is the longest delay, and then understandably that gives us the lowest dip in our flyaway height procedure. And we can see here that the rate at which you put on that nose down, okay, really makes very little difference to the height that you lose during the flyaway manoeuvre. So we know that delay is bad, but the rate that you put the nose down on is really somewhat irrelevant. So that means rather than having to do a very hurried push forward to get your nose down, we can use a much slower cadence of adopting the flyaway attitude that we need. So those are the kind of tools that we can use, the automated analysis. Another very useful feature is to be able to get in as pilots and actually fly the techniques and see how they go. So I've got a couple of videos here. You'll hear one of the simulator team, hopefully on the audio if it works, calling out rotor speed. So the 99, 97, 98, 94 is the rotor speed. You'll hear them mention 40 feet as well at the bottom. And then I'll show you another video using a different technique. But this is the kind of best technique that we've got at the moment, if you like.
Torque spin. 199,
Rotor,
97,
rotor.
94, 95, 96, 97,
Engine
98,
fail.
97, 96,
Caution.
95, 94, 94, 95.
Rotor,
Going
rotor.
through 40 feet, 94, 96, height
Engine
steady,
fail.
97, 98, climbing
Check
away.
height. Warning. Engine fail.
So in that case there, we could see good management of the rotor speed. He contained the rotor speed around 94, 95, 96%. He adopted the accelerative attitude, the aircraft built the speed and flew away safely. So this is a bit of an extreme because I wanted to show the comparisons. But in this next example, effectively the pilot is not managing the rotor speed at all. He's allowing the rotor speed to decay. So how much difference does that make? Well,
Recording. Debriefs. Recording. Torque spin. Flying away. 99, 96,
Rotor,
95, 93, 92, 91, 90, 89,
Engine fail.
88, 87,
Caution.
87, passing 70 feet, 86, 87,
Rotor.
80.
so you can see in that example there, with the rotor speed not managed correctly, okay, the aircraft hits the ground quite hard, so no flyaway at all from effectively the same entry parameters. So we can play tunes on those techniques that we're using to try and find the optimum technique in the simulator before we go and try it in the aircraft. And then when we get in the aircraft, we know what we're looking for when we start changing some of those parameters to help us. Another good use of simulators is visual cues. So the model might suggest a profile for you to fly, for example, coming back off a helipad, where you can't actually see the helipad because the angle that you're being encouraged to come up at is too steep. So this is actually pictures from the real aircraft, but these were developed in the simulator, where we were able to use the visual cues on the side of the aircraft to pinpoint where the landing site should be. So when we're going away to fly those profiles, we can very accurately judge and repeatedly fly those profiles and then vary them accordingly to find which bit of data is going to give us the best outcome. Right, in my intro scope, I said I was going to discuss some of the challenges that we have of practically flying these types of flight trials. So all-up mass is one of them. If you're trying to target performance within a certain mass band, the only way we can do that is by going for a refuel. So sounds simple, doesn't it? But the amount of time we use trundling over to the other side of the airfield to get some fuel, and then EasyJet shows up, or the fuel man's gone for his coffee break, etc., 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 causes a lot of delay and friction within trials. So trying to manage that all-up mass is a real pain for us. We also have issues where you're jumping around between different data points. You've got to ballast the aircraft, deballast the aircraft. So these sort of things just friction within trials. And so when people say, why is it taking that long? Well, these are the kind of reasons that it does. Temperature, obviously over the day, the temperature will start relatively cool and then gets warm. That means you've got to adjust your data accordingly. And so when you're comparing things with things, there might be some errors that are brought in from the data. Engine degradation, I spoke about at the beginning, so that's another factor of the engines that you've got fitted to that aircraft in that day. You know, what is their performance index on that particular day, and are you calculating for that appropriately? Flying repeatable flight techniques, so I kind of showed some of the challenges of the pilots having to fly the same technique over and over again. But as I said, in some ways that works for us because we do get some scatter. And then wind. So wind is probably our biggest issue. In order for the data to be pure, we need the wind to be below 3 knots. So the first problem is where do you go in the world where it's consistently at 3 knots or less? And the answer to that is, well, there aren't very many places that offer that reliable low-speed wind for us to be able to do our performance testing. And to get that, when we do go somewhere, we often end up getting up at 4 in the morning to start our testing just as the sun comes up, because clearly the wind that we have in the morning is generally calmer. But we then find that as the day goes on, testing has to stop because the wind will start gusting up to above 3 knots. We also have the problem of you've got a helicopter that makes downdraft, and that wind effect of the downdraft means that you can't have an anemometer nearby because it's disturbed by the airflow of the helicopter, but you want to know what the wind's doing exactly at the helicopter. So it's a constant battle of trying to get accurate wind. And the picture here shows our latest development, which is a laser-based wind detector. That's very useful for us because we can select the height that it measures the wind at, because it's using a laser to gather the air data, so we can match the data of the wind to the height of the aircraft, rather than the old days where you just had one boom anemometer stuck on an airfield. So that's one of the technologies that we're using, and we now have that fitted to a mobile or to a vehicle, so it's mobile and we can move it around the airfield to try and find the optimum position so that we can accurately measure the wind while we're collecting performance data. Right, coming towards some of the other innovations that we've got, we also now with advanced engine control, electronic engine control, we can ask the engine manufacturers to alter the FADEC control of the aircraft such that when we are simulating these engine failures, we can get the engines to respond in the way that they would do for real. So if you remember earlier, I mentioned this max continuous power of about 100% and max contingency of an engine running up to 130, 140%. So clearly on a trial, you can't keep dragging an engine up to that 140% maximum contingency limit, because basically the wear that you put into the engine is excessive, and then you have to reject the engine within not many hours of flying. So in the past, what was done was the power was limited at your max continuous level, and therefore you had a slightly warped sense of reality. What we can do now is use the FADEC engines to give us a more representative power when we suffer the engine failure. So just have a quick look at this graph here. You can see this is rotor speed decaying, and you can see here that this is the collective position. So the pilot checks down on the collective lever in order to allow the rotor speed to increase again. So that's interesting. That's kind of what we were expecting. If we look at this slide here, this is a similar condition. But at this point, the pilot doesn't check down on the lever. He holds the lever steady. Now, any helicopter pilot would tell you what they'd expect is once that rotor speed is decaying, it would continue to decay, and you would not be able to restore it. But what we can see here is that we've got the FADEC file in. So what that does is this is actually for a Merlin, so it's 3 engines. But we've got 3 engines running, and when one fails, rather than failing all the way to 0, it drops and then replicates the running up of the 2 good engines, so that now it's adding in an extra 50% torque. So our 2 good engines plus our failed engine is now giving us that contingency power as it would do for real. And we can see that in this case is a really good example where it shows that actually with that full power it restores the rotor speed back up without the pilot having to lower the lever. So really kind of interesting data and providing that realism that we want. Right, how can we further refine our flight testing? And so one of the things that we've developed at Leonardo is a new feature for the AW101 digital flight control system, where you can automatically get the aircraft to fly your flyaway maneuver for you. As I said, pilots aren't always brilliant at it, whereas if you're doing it with a digital system, it can be far more accurate. So that is a selectable mode. The pilots get into the hover position that they want. They then select flyaway mode. And then basically the aircraft will respond and conduct a flyaway when it senses an engine failure. So you can sit there hands-free as a pilot and get the aircraft to fly for you. So here's some data from that. We've got effectively the green line is the computer, is the flight control system. The blue line is the pilot. So you can see here in this trace, this is lever position, collective lever position. So you can see the flight control system instantly goes into the correct position to get the rotor speed exactly how it wants it at the optimum of 95. The pilot in the blue line has a couple of goes with the lever, moving the lever around, which allows a big fluctuation of the rotor speed and doesn't allow a nice, smooth, steady decay. Similarly up here, you can see with the pitch of the aircraft, the flight control system controls the green line very quickly, smoothly, accurately down to a 15 degrees nose down flyaway attitude. The pilot, okay, a little bit slower and just a little bit more waffly in trying to nail that 15 degrees nose attitude. So what does that give us overall? You can see here for the height loss for 950 feet, the computer flies away within 100 feet. The pilot starting at 900 feet comes all the way down to 650. So a considerable difference in height loss from the automated system to the pilot flying. Probably the worst example I could find. The pilots aren't always that bad, but I wanted to show you how that automated flight system is another step, another tool in us achieving the flight test data that we want. You can see here, this is a graphical representation of what I've just showed you. So this is the flight control system. You can see that the loss of height in the initial stages of that is really quite minimal. That's because it's nailed the attitude and the rotor speed. Whereas the real pilot flying, you can see in the early stages, the delay and the mismanagement of the rotor speed combine to give you that height loss. So, yeah, all good. Okay, that kind of wraps up what I wanted to talk about. We are taking the Norwegian AW1 out to AW101 out to Norway in a month to start a trials procedure looking at performance at 5,000 feet, where we'll be using many of the techniques that I've discussed here and the little advances that we've made now to test the aircraft and develop the performance figures and refine the Category A Class 1 flyaway procedures from what we have already, and do that spot check of the envelope out to 5,000 feet. So that is the next step for Leonardo and where we're taking the aircraft. To summarize then, we talked about flight tests. I wanted to keep it very practical. I hope I haven't lost you with some of the terminology that we've used. But effectively, we start with a model. We then validate the model. The model then gives us our suggested flyaway profiles that we can use, and we can then use the simulator to help us, but then go away, and it all comes down to live flight test data. And the video that I showed you of the yellow helicopter out there in the sunshine, that was actually out in Italy. So we have 587 videos of helicopters doing that kind of stuff taken over a 4-week trial period. So it's very repetitive. We collect a lot of data, and then we use that to fill in our model, correct our model, and then produce the figures and advice for the pilots flying when they suffer an engine failure, so that hopefully, unlike the seeking, they don't end up hitting anything and crashing, but they can use those correct techniques from a safe position in order to ensure they can recover the aircraft safely. Right, that's me, 45 minutes, so over to you for anybody that's got any questions.